Hello everyone, moving charges and magnetism part 3. In this video, I will be discussing the Ampere Circuital Law, the magnetic field due to a solenoid toroid, and the definition for ampere, which is the unit of electric current. First, we shall see the Ampere Circuital Law. For that, consider a closed loop C around a current carrying conductor in which the total current flowing is I. Now, according to Ampere Circuital Law, line integral B dot dl is equal to mu 0 I. That is, the line integral of the magnetic field around some closed loop is equal to mu 0 the times the algebraic sum of the currents which pass through the loop. In 1826, Ampere demonstrated the above equation holds for any closed loop which circles around any distribution of currents. Ampere's law is a useful relation that is analogous to Gauss's law of electrostatics. It is a relation between the tangential component of magnetic field at points on a closed curve and the net current through the area bounded by the curve. Now we can see the proof of Ampere's law. For that, we can consider a current carrying conductor having a current I flowing through it. Now it is required to find the magnetic field at a point P. For that, we can consider a closed loop of radius R. The magnetic field is tangential to the point P, and dl is a small element at point P. Now by Biot-Savart law, B, which is the magnetic field, is given by mu 0 I by 2 pi capital R. Therefore, the line integral of B dot dl is equal to line integral of mu 0 I by 2 pi capital R dot dl is equal to mu 0 I by 2 pi capital R line integral of dl. The line integral of dl is equal to 2 pi r, the circumference of the circle. Now substituting this value, we get the line integral of B dot dl is equal to mu 0 I, which is the Ampere Circuital Law. If the wire lies outside the Amperian loop, the line integral of the field of that wire will be 0. But does not necessarily mean that magnetic field is 0 everywhere along the path, but only that no current is linked by the path. While choosing the path for integration, we must keep in mind that point at which field is to be determined must lie on the path, and the path must have enough symmetry so that the integral can be evaluated. These points have to be kept in mind while using the Ampere Circuital Law for finding the magnetic field. Now we can see this solenoid. By long solenoid, we mean that the solenoid's length is large compared to its radius. It consists of a long wire wound in the form of a helix, where the neighboring turns are closely spaced. So each turn can be regarded as a circular loop. The net magnetic field is the vector sum of the fields due to all the turns. Enameled wires are used for winding so that turns are insulated from each other. This figure shows the solenoid. In figure A is shown a stretched view of the solenoid. We can see that the magnetic field is through the axis of the solenoid. And in the figure B, the whole magnetic field lines due to the finite solenoid is shown. Now we can consider a small Amperian loop ABCD along a section of the solenoid as shown. Since the sides of the loop AD and BC are not in the direction of magnetic field, no magnetic field exists along these two directions. So, the magnetic field only exists along the AB side. Now let the field along AB be B and total number of turns is NH, where N is the number of turns per unit length. Therefore, the enclosed current IE in this Amperian loop is equal to I into NH. Now by Ampere's circuital law, we know that line integral B dot dl is equal to mu 0 I, that is B into L is equal to mu 0 IE. Here L is equal to H. So BH is equal to mu 0 INH, or B, the magnetic field due to the solenoid is mu 0 Ni. In this case, we can see that the magnetic field at Q is 0. The Q is a point which is external to the solenoid. Now we can see the toroid. The toroid is a hollow circular ring on which a large number of turns of a wire are closely wound. It can be viewed as a solenoid which has been bent into a circular shape to close on itself. This is a toroid. In this case, there is no magnetic field at points P, which is inside the toroid loop, and Q, which is external to the toroid. Now for finding the magnetic field due to a toroid, we can consider the cross section of a toroid. And we can consider 3 Amperian loops. The first loop is inside the toroidal loop, enclosing P, and is of radius R1. We have already seen that there is no magnetic field inside. This is as a result that no current flows in that region. Similarly, for loop 3 also, the magnetic field is 0. Since the currents flowing in that region are in opposite direction and cancel out each other. Now, for loop 2, by Ampere Circuital Law, let it be B, the magnetic field, into 2 pi r, where R2 is taken as R is equal to mu 0 into N into I, where N is the number of turns of the toroid. Therefore, B is equal to mu 0 N I by 2 pi r. Capital N is equal to 2 pi r N, where 2 pi r is the average perimeter of the toroid and small letter n is the number of turns per unit length. Therefore, the magnetic field is equal to mu 0 small letter n into I. Now we can see the force between two parallel currents, and by using the result of this derivation, we can define the unit of current, the ampere. For that, we can consider two conductors A and B, which are separated by a distance d. In these two conductors, two currents, namely IA and IB, are flowing in the same direction. Now, the magnetic field due to A at a distance d is given by BA is equal to mu 0 IA by 2 pi. The conductor B experiences a force FB due to the magnetic field. And the magnetic field direction can be found out using the right hand thumb rule. Now for length L, as shown in the figure, FBA, which is the force due to A on B, is equal to IBL BA. That's equal to mu 0 IAIB by 2 pi d capital L. Similarly, FAB, which is the force on the conductor A due to the magnetic field produced by the current flowing in conductor B, is found out that FBA is equal to minus FAB, which is equivalent to the Newton's third law. In this case, currents are flowing in the same direction. Hence, there is a resultant attraction between the two conductors. This can be seen by analyzing the direction of the magnetic field by using the right hand thumb rule. When the currents in the two conductors are flowing in opposite direction, these two conductors repel. Now we shall see the ampere definition. The ampere is the value of that steady current which, when maintained in each of the two very long straight parallel conductors of negligible cross section and placed 1 meter apart in vacuum, would produce on each of these conductors a force equal to 2 into 10 raised to negative 7 newtons per meter of length. The definition of the ampere was adopted in 1946. It is a theoretical definition. In practice, one must eliminate the effect of the Earth's magnetic field and substitute very long wires by multi-turn coils of appropriate geometries. An instrument called the current balance is used to measure the mechanical force. Now we can define Coulomb, which is the unit of charge in terms of ampere. That is, when a steady current of 1 ampere is set up in a conductor, the quantity of charge that flows through its cross section in 1 second is 1 coulomb. So this is the end of this video. In this video, I have discussed the Ampere Circuital Law and used it to calculate the magnetic field in a solenoid and a toroid, and also have given a theoretical definition for ampere. If you have got any doubt, please comment in the section below. Thank you.